Good morning. My name is Bob Mickelson. I'm the moderator for the session, Quantum Computing, a Technology for Complex Problem Solving. Quantum computing is an exciting emerging technology. It is my privilege to introduce our speaker, Chantal Tsang, who will provide you a basic understanding of how quantum computers work, current status of the technology, and what its future holds for complex problem solving. Chantal is an assistant professor in the Department of Electrical and Computer Engineering and the College of Optical Sciences at the University of Arizona. He joined the university after finishing a position as a postdoctoral fellow at the University of California, Berkeley. He earned his Bachelor of Science degree at Peking University and his PhD in physics from the Massachusetts Institute of Technology. The University of Arizona was recently awarded a 5-year, $26 million grant from the National Science Foundation with an additional 5-year, $25 million option to move now to Chantal's presentation. Thank you.
Hello, everyone. I'm Chantal Zhuang. I'm assistant professor at the Electrical Computer Engineering and Optical Science at U of A here. And I'm glad to talk about quantum computing as a new technology today. And thanks, Bob, for inviting and introducing me. And so I'm going to share screen and start my talk. I'm Chantal Zhuang. Okay, so you probably have already heard that quantum computer science is really booming these days, and especially at the U of A here. Recently, U of A was awarded the so-called Center for Quantum Internet. It was a NSF funding, and it was one of the engineering research center. And the overall goal is to develop quantum networks. And so if you think about classical computers, the internet is really very important for making things work. For example, this conference can happen because we have internet. And the goal of this center is to build the quantum version of this internet that not only enable the sharing of classical bits, but also the sharing of quantum information. And this is a very challenging task. And U of A here is teaming up with Harvard, MIT, and Yale and others to develop the technology and also the related policy and other things related to quantum networks. Moreover, this is the U of A team of this ERC center. And as you can see, we are doing the social distancing, and we hope that the COVID-19 can end soon and everything can come back to normal life. Moreover, more recently, there was this DOE center that aims at building quantum computers. So we are participating as collaborators, and Fermilab is leading this center. This is an even larger investment of 115 million. And the goal is to use different platforms and mainly superconducting to build a quantum computer and solve very difficult problems. And our role in this center is to develop novel quantum sensors and error correction codes to facilitate the development of quantum technology. So let's start from the basics. I'm a physicist, so when I think about quantum computing, I want to start from physics. So the goal of physics is to understand nature, and we know that quantum physics has been there for some time, and it really takes great people like Schrödinger, Einstein, and Stephen Hawking to figure things out. And for example, you probably have already heard of those so-called Schrödinger cat, and it is indeed a cat, but it's a cat at the superposition of life and death. And this is basically one of the scenario where a microscopic object can be in a superposition of two states. And in fact, today we can actually engineer a pretty large object in superposition. And Einstein have come up with the question, can entanglement really happen? This so-called spooky interaction at a distance. And nowadays we can verify that entanglement indeed exists, and we can make use of entanglement to do a lot of things, as we will talk about later. And Stephen Hawking worked on the black hole information paradox, and it also gives a lot of insights into quantum information science in general. However, as Richard Feynman has already said some time ago, if you think you understand quantum mechanics, you don't understand quantum mechanics. Well, this seems contradictory, but my interpretation is that as quantum physics is so counterintuitive that it is very different from everyday life. So you will never stop confusing yourself with new questions. Whenever you think you understand, sometime maybe new scenario happen, and then you find that you need a new fresh up of thinking. So there's never an end of really understand what is quantum mechanics, but we can think as engineers, and if we can use to predict experiments and we can use it for engineering purposes, that means we might have understood most of it and make use of it. Indeed, today we are already at the era of quantum engineering, and roughly speaking, the quantum technology can be classified into three categories: quantum sensing, quantum communication, and quantum computing. And in quantum sensing, we will use non-classical resource to enhance hypothesis testing and target detection processes. For example, the famous project LIGO is one of the examples of quantum sensing. In quantum computing, there were different platforms, for example, adiabatic algorithms, circuit model, or measurement-based quantum computing. And many big companies are heading at this quantum computing direction because it really solves realistic problems. And solving this problem will be very useful. For example, Google has invested a lot on achieving the quantum supremacy experiments. And IBM has a 50-qubit quantum computer as well. In quantum communication, there's a lot of investment as well in quantum teleportation, quantum network, and quantum key distribution as well. And these three domains are actually closely related and very closely connected. For example, in quantum sensing, you need technology from computing to help you build receivers. And in communication, you need encoder and decoders, which are sometimes enabled by quantum computing. It's just like the classical case where those sensors are all wired to an internet, and then sensors will need quantum computing, classical computers to really decode or compute or doing data processing to get the overall result. And this is the same case for the quantum. So the most famous example of quantum computing you probably heard is the factoring problem, where the goal is to solve the problem of factor a large number n into the multiplication of p and q, two numbers. And for simplicity, we can consider p and q both to be odd number. So in a classical computer, the best known algorithm is called general number field sieve, and it solves the problem in a very long time. So if you write down the expression precisely for n-digit number, so if, for example, 100, it's a 3-digit number, so small n equals 3. That's the decibels. So if you write down the bits, then let's say 8 is actually 100 in binary digits. Therefore, 8 has 3 digits. note that this is log 2n. So in terms of binary digits, if you have n digits, then the classical algorithm needs to take exponential of n to the third with a log prefactor overall. So roughly speaking, it's going to take exponential in number of digits to solve the problem of factoring. But there's a famous quantum factoring algorithm that solves the problem of factoring in time polynomial in number of digits, which takes n squared with some log prefactor. So let's take an example. If you have 100 digits, which is a pretty large number, then here it's going to be exponential of around 100 to a third power. If it's a square root is 10 to a third power is probably around 6. And 6 times this is going to be 12, and exponential to the 12, it's going to be a large number. So let's think about 3 to the 12th order, 12th power. It's going to be, let's compute it. Okay, 9 squared 81. Okay, give up. It's a very large number. But if it's just n squared, then it's just 10 to the fourth. So this can be 10 to the 10 or even larger, and this is 10 to the fourth, and it's a big difference. And the difference will become even larger when n is large. Okay, so it sounds very promising. We can solve difficult problems, and factoring is one of the NP problems, although it's not NP complete, but yeah, it's considered to be average case hard. The conjecture to be average case hard. However, it's very hard to build a quantum computer, and as you know, so far we don't have a fully error-corrected and programmable quantum computer yet. And our demonstrations so far in the field, in the whole quantum community, is to factor numbers smaller than 100. So you and me can factor 100 in the head. So not very powerful, right? But this, if we expect quantum computers to really be built, this will be the most, actually one of the most impactful algorithms in quantum computing. And there's more. People have developed multiple and countless quantum algorithms in the almost a decade or 20 years, including there are quantum algorithms solving partial differential equations, quantum algorithms for solving data classification. And here's a review paper by these guys. They basically summarize the application of quantum computing in machine learning applications. So in this table, they carefully listed all the machine learning algorithms that can be speed up by quantum computing, by quantum computers. So for example, this Bayesian inference, and then you have Boltzmann machine, you have principal component analysis, you have a support vector machine. So you have everything here. So a lot of these algorithms, once you can build a quantum computer, you can speed up with some advantage. Sometimes it's a square root of advantage. If you think about it, it's actually huge. If the original algorithm takes 10 to the fourth steps, and then if you take a square root, it's going to be 100 steps. It's going to be a very big difference. And this log improvement is even better. If the original computation takes about maybe 100, then if you take a log, it may be just below 10. And also people have different, also there's an alternative way of designing algorithms, which is called quantum annealing. And this makes use of quantum tunneling effect. So you may have heard about it. So when you do optimization, you're basically minimizing overall cost function. You want to find the global minimum. And when you find this global minimum, you can use the classical Monte Carlo simulation, or maybe it's called classical Metropolis algorithm, where you try to throw random points, and then these random points do local search and do this annealing algorithm of jumping around. And in the end, they might be able to jump to the global optimum. But these local minimums will be the obstacles. So often you will be trapped at a local optimum, but quantum tunneling can help you jump through these barriers and find the global minimum more easily. And in this algorithm design platform, then you can basically consider all kinds of optimization and try it on the quantum annealer and find out whether there were speed ups. And there were a lot of search relativities. In theory, there should be speed ups, but in experiments, there's probably, I think, to my knowledge, there's no confirmed speed up in annealing yet. At least not well accepted by the whole community. It's ongoing research. So there are so much difficulties. So what should we do? Okay. So John Prescue, in this famous paper, proposed this term called noisy intermediate scale quantum technology, or short as NISQ. And the title is called Quantum Computing in the NISQ Era and Beyond. So it tells us what we can do with this noisy, non-perfect device. And so it is likely that quantum computers with 15 to 100 qubits may be able to perform some tasks that better than the classical computers. But what are those? We want to identify them, and we want to try to achieve that. And that is what Google actually have done in the recent Supremacy experiment. So this is the famous paper published in Nature by Google Quantum Group. There's a lot of authors, and it's led by John Martinez. Okay, the title is called Quantum Supremacy using a programmable superconducting processor. And it's a very accurate title because it's using the word processor. It's not yet a fully programmable error-corrected quantum computer yet. This is a schematic of the architecture. Basically, every cross is a qubit, and then you have these couplets between the qubits. And these couplets can be programmed and tuned so that these qubits can talk to each other and perform gates. So this is basically can be used to implement quantum circuits in a controlled way. And the so-called quantum supremacy is basically saying that, okay, doing this task in a quantum computer will take much less time than the classical computer, which is often formidably hard, very hard to solve. And this is the performance curve. And this is the cross entropy benchmark fidelity, meaning this cross benchmark is for verifying whether this distribution is the same. Okay, maybe that's too technical. Anyway, we'll come back to that later, but this is basically verifying the performance. And this is the number of qubits. So as the number of qubits increases, it takes longer and longer to verify in the classical computer, or in other words, to do the same computation on the classical computer of what the quantum processor is able to. So at this point of 52 qubits, I think, or 53 qubits, it takes 5 hours for classical verification, while it takes much less time on a quantum computer. And this grows even more drastically when you increase the number of cycles. So there were two parameters for the probability scale. One is the number of qubits, that's how many qubits you're acting on. And then there's the parameter of number of cycles. So how many gates or how many runs of computation you're applying on it. And the more the cycles, the longer the computation takes on the quantum machine. And it takes drastically longer on a classical computer. So here, it will take, for example, 1 week, 4 years, 600 years. and even much longer. And there are other improved algorithms, but it also takes a long time to achieve. For example, at this point, it will take estimated to be 10,000 years for a classical computer to complete, while for quantum computers, they complete the experiment in 200 seconds. So, or yeah, I think it's 200 seconds here. So, and for the 10,000 years, it's actually considering a million core already, meaning it's a supercomputer that takes 10,000 years. So it is really not really computable classical machine, while it takes 100 seconds on this Google device. Wow, that's very remarkable, isn't that? And it is indeed very remarkable. And you probably have a lot of questions on this, and there were so many media coverage on it. And I think John Preskill, who wrote a paper of niche quantum computing, I think there were television shows, I think, asking him questions, and there were also a lot of other media coverages on what's the impact and what really happened. So here, let me try to explain some of the questions that which you probably will come up in your mind. And these questions and answers are taken from Scott Everson's blog. So Scott Everson is a researcher in quantum information science, and his specialty is in quantum complexity and quantum algorithms. He is currently at UT Austin. He used to be at MIT, and back then when I was at MIT, we attend a lot of discussions and group meetings together. And I was a student back then. He was at MIT, and he is a very smart person. He has a lot of very precise and sharp perception and remarks about other people's works. And I think here, using his comments will be more professional than mine. And yeah, so let's go into that. First question: what is quantum computational supremacy? Well, supremacy might not be the best word, but somehow we just use this word, quantum supremacy. It really means that there are some well-defined problems, for example, factoring or optimization, some kind of optimization problem. And it's well-defined, and however, it takes very, very long time to solve on a classical computer, while it takes much less time on a quantum computer. And this makes it reasonable or practical to implement it on quantum computer, however, not practical to implement on a classical computer. And this disparity we call quantum supremacy. And the second question: if Google has indeed achieved quantum supremacy, does that mean now no code is unhackable, or no code is uncrackable? Means, okay, so now that we have supremacy, quantum supremacy, can we solve all the problems? Can we solve all the hard problems? The answer is simple. It doesn't mean we can solve all the problems. No, it doesn't. So there were two issues here. First, roughly speaking, Google's device is not error-corrected, meaning it's the best analog would be a classical analog device. So there's no error correction. It's a circuit that implements some input-output relation, but it's not really robust, and you cannot really scale it up very easily. And moreover, it cannot really implement those algorithms that is delicately designed to speed up classical problems. It's not a quantum computer yet. It's special purpose device. So it doesn't solve all the problems. And in fact, it only solves very particularly designed problems. And the second issue is that even if we have a fully error-corrected quantum computer, fully running quantum computer and very large quantum computer, we cannot solve everything. At least we don't know that we can solve everything. It is unlikely we can solve everything. Therefore, there were other so-called post-quantum cryptography protocols that quantum computers cannot break. And frankly speaking, the only thing that we can break is all most related to factoring, which is the RSA protocol, named after the three famous inventors for the encryption. So there were lots of other problems we cannot solve, and you can use those problems to do a crypto system. And if we have quantum computers, we cannot break those. So if a media or some news coverage say, quantum computer can solve everything, it's not right. Quantum computers can solve some hard problems, but its power is also very limited. And we have very credible crypto designs to be safe against the quantum computers. So what exactly is the calculation that Google is doing or planning to do or has already done? And that's believed to be classical heart. It's a long answer, and it's really a long story of the problem, because it's not a universal quantum computer yet. So it's really a very specially designed task that Google device can complete. It's the best and classical analog is probably classical random number generation. So as you may know, in a classical computer, you cannot generate real random numbers. Classical computers generate pseudo random numbers. So how to tell whether the random number is really random or just pseudo random? You have a lot of benchmarks. So you have to pass all those benchmarks to be a real random number. And it is actually difficult to generate random numbers. Although you may think, okay, I can just give you random numbers out of my head, but if you do it that way, it's not really random. It's probably someone can easily crack the way you generate random numbers. To really generate good quality random numbers, you really need to design a very particular way of doing that. For example, some classical device rely on some physical process that is considered random, some fluctuation in some chaotic systems, but it's really hard. And so this quantum device, what it does is to generate very special quality random numbers. So it's going to generate n bits, let's say n classical bits, and these n classical bits are correlated in a certain way. And correlation means that, for example, if it's 100% correlated, then I get identical outputs on all the n bits. It's all 1 or all 0. That is very simple correlated. But in this case, the random number that Google computer or Google device generates is very special. It has a very complicated property distributions, and it's very hard for classical computer to generate that random number and pass those random number tests. So if you just write up an algorithm to generate that random number, if it's a crappy algorithm, I can set up some benchmarks and easily tell that it's a crappy random number. It's not a precise distributed one. So in order to generate the correct random number, it's very challenging. And this random number generation task is what Google has done on this quantum supremacy test. And it takes a long time for a classical computer to generate the random number. So question 4, if the quantum computer is just executing some random garbage circuit whose only purpose is to be hard to simulate classically, then who cares? Is this a big overhyped nothing burger? Basically, it's saying, okay, it's a random number generator. It generates random number. So why is random number useful? Well, it is useful, but not very useful. That's true. So as Scott Arizon's answer here, it's not an everything burger, but it's certainly at least a something burger. So quantum supremacy of Google achieves something that is remarkable. It did something that a classical computer cannot do, but it does not solve a very useful problem yet. But it's a good sign. So I mean, in the future, people might well find other applications where devices like this one that Google has developed can be very useful at. So it is really a first demonstration instead of an end point. So the search for a quantum device that really gives you practical advantage in solving hard problems, we should think about it as just started, not ended, certainly not ended. There's still a long way to go to build a fully error-corrected computer to do all this factoring and other machine learning algorithms. Another question, if quantum supremacy calculations just involve sampling from probability distributions, how do we check that they were done correctly? So this is a bit technical question. Basically, you need to try to find whether there's a pattern in the random number. And so people doing computer science and doing statistical theory, they have a very well-developed ways of doing benchmarks. For example, use this cross-entropy benchmarks to test whether this random number obeys that distribution. And I think I'm not going to much of detail here. The short answer is that there's a set of very rigorous checks. This Google calls linear cross-entropy test. And it's convincing in the sense that I think well-trained statisticians won't object. So if classical computers can only track the results of quantum supremacy experiments in a regime where classical computers can still simulate the experiment, then how do you get to claim quantum supremacy? That's a very good question. So the thing is that when problem is so hard, we never know that the quantum computer is still doing what we expect it to do because we cannot really check. So when the problem is small, okay, it's like you're coding a classical computer to solve a problem, and in a small scale, for example, factoring. In your head, you can factor 15 equals 3 times 5, and then you input 15 to that algorithm and see if it outputs 3 and 5. If it does, then it succeeds. And you can continue doing this for larger numbers, maybe, for example, 121 equals 11 times 11. You can do it in your mind while you input it in the computer, it gives you the correct answer. But when it increases larger and larger, you cannot really come up with the answer in your mind. So at that point, how do you tell whether two numbers coming out of the classical algorithm is correct? For factoring, it's good because you can always multiply to verify that in polynomial time. But for this random number generation, there's no good way of verifying it is indeed the right answer. But So the speed up is growing exponentially with the number of qubits, exactly as syntactically analysis would predict. So basically, it's saying that you can keep track of how it evolves as the number of computations increases, and you can look from the scaling whether things is correct, and there you can you can perfectly conclude that you see a speed up. Is there a mathematical proof that no fast classical algorithm could possibly spoof the result of sampling-based quantum supremacy experiment? No, not at present. So there's no rigorous proof that we cannot solve the classical problem efficiently, meaning we don't know whether there exists a good classical algorithm to solve it. But that's the often case. It's just like we cannot prove the P equals NP, or we cannot disapprove P equals NP. These kind of questions. So it is widely conjectured and expected in the case that P is probably not equal to NP. And it is also in the same way conjectured that there's no fast classical algorithm that can solve those quantum supremacy experiments. Although they are all conjectures, but they are very well-founded conjectures. And these conjectures are actually the foundation of our current crypto system. And so far, most of the crypto systems works well. And those doesn't work well really actually from human errors. For example, human leak of the codes. Yeah, to clarify the last question, actually, so you can still find a good regime where it takes very, very long time on your classical computer, supercomputer to solve, and then you can solve it very easily on your quantum computer. So there's already a very huge disparity of the time it takes to solve the problem. So in that sense, you already see that in a supercomputer, it takes so many number of CPU hours to solve, while on a classical computer, it takes 200 seconds. So isn't that a supremacy? Okay, applications, I think I already covered this question. So does sampling-based quantum supremacy have any applications in itself? I don't think there's explicit applications yet, but there may be there may be applications related to crypto systems or random number generation. And I believe in the future, people will find some good applications for this kind of devices. Okay, so much for quantum supremacy. So what's next? So Google's quantum supremacy experiment is an exciting achievement. However, it is not a free arithmetic quantum computer. It's not like your PC you can use to solve real problems. So the next 10, 20, 50, 100 years ago would be to build a quantum computer with error correction and to have around 50 to 100 logical qubits and to realize all kinds of quantum algorithms. With error correction, that will probably take maybe 1,000 or 10,000 or even larger number of qubits. So we are still a bit far. So I'm really not sure how many years it will take. But there's no physical principle that prevents us from building a large quantum computer. So it's all about engineering here. Okay, so these are the applications and the state-of-art of quantum computer. But meanwhile, in the NISQ era, in the noisy device era, can we do something useful that is something really practically useful? Well, the answer is yes. So for example, the famous LIGO system or laser interferometer gravitational wave observatory system that is used for sensing gravitational waves that recently lead to discovery of black hole mergers and a lot of and the verification of Einstein's general relativity and gravitational wave. So in fact, the LIGO system has already implemented so-called squeeze light to suppress the measurement noise. And this squeeze light is a non-classical quantum effect, and it's one of the quantum technologies. So things like that will be very useful in quantum sensing, in sensing applications. And other scenarios involves this so-called variational quantum eigensolver. And what they do is they can sort of do some variational circuit and then do some optimization to solve the eigenspection of molecules. And there's no proof for speed up, but it seems that there's some speed up, and hopefully along this path, when we build some noisy intermediate device, we can actually implement something useful. And also here at U of A, we are actively working on utilizing quantum technology to enhance other practical tasks. For example, we recently developed this distributed sensing technology for enhancing radio frequency signal sensing, and potentially this can be used for improving the precision for GPS and other sensors related to RF signals. So basically, it utilizes multiple time entanglement among different sensors, and the more sensors you have, the more advantage you can get from quantum entanglement. And this has been we did a theory, and then with collaborators, we also did experiments to verify our theory in these applications. Also, we have other works on utilizing these quantum sensing ideas to improve these so-called physical layer supervised learning problems. So, for example, if you want to solve a classification problem, but the thing being classified is molecules. For example, you have a couple of unknown molecules. You want to find some unknown, what is the unknown molecule? Then you use a bunch of sensors to detect the molecule. And then you can perform measurement on the return or after the interaction with the molecule, you can measure the remnants. And then you use classical processing to determine what's the class of the molecule. And this setup, you can use quantum sensing technology to improve the performance. So to conclude, we are at the era of quantum engineering, and with quantum sensing, quantum communication, quantum computing as the three pillars for quantum technology. Although we have not developed the fully error-corrected quantum computer yet, but we have already demonstrated, the Google experiment have already demonstrated the quantum supremacy that classical calculation power cannot achieve. And we still have a lot to achieve in quantum, and I hope you find my talk interesting. So if you have questions, feel free to give it to Bob or send an email, and I can send an email and communicate later. Okay. Thank you for your attention. Bye.